Welcome. Today we look at section 3.2, more set operations. Three things we can do with sets. We have 1, Cartesian products, 2, power sets, and 3, set partitions. Number 1, Cartesian products. Suppose I have a set A and a set B, and A can be any set really, as can B, and I will combine them with the Cartesian product of A and B. We might read this as A cross B. It is a set of ordered pairs, and the first component of each ordered pair is taken from A, and the second component of each ordered pair is taken from B. And we do this with all possible combinations. In general, the Cartesian product of A and B is A cross B equals all ordered pairs of the form AB, such that A is taken from set A and B is taken from set B. So how about the sets A, which is 2, 3, 4, and B, which is 3, 5? Can you create the set A cross B and B cross A and this other one on the bottom, and how many elements are in those sets? Take a second, work it out, pause the video, and then start up again when you are ready to check your work. Alright, so A cross B. Well, there are 3 elements in A, 2 in B, and in fact there is 6 altogether in the Cartesian product. The Cartesian product of B cross A, it's a slightly different set, but the same size. And then A intersect B, so what is that really? That's just the set containing only 3. And A union B, that's the set 2, 3, 4, 5. 4 elements in there. 1 times 4, there's 4 elements in the Cartesian product. 2, power sets. Let's say we have a set A, which is 1, 3, and 5. I'm going to create the set that is the set of all subsets of A. And it's called the power set of A, and that's a script P in front of the A. So script P of A is the power set. Notice a couple things. First of all, the entire set A is in there. So A is a subset of itself. This is a true statement. A is a subset of A. So this whole set, 1 through 5, is one of those elements. And then we have all the proper subsets. And then we also have the empty set, because the empty set is a subset of every set. So in fact we end up with 8 subsets in there. So the power set of A has 8 elements. In general, we could write the power set this way. The power set of A is the set of all sets S such that S is contained in A. How about these 3 examples? Again, let A be the set 2, 3, 4. Let B be the set 3, 5. How many elements are in the power set of A, the power set of B, and the power set of the intersection? Take a couple seconds, figure out what those sets are, what those power sets are, and how many elements are in each. Alright, start up again when you want to check your work. Let's see. So this is the full set that's the power set of A, and there are 8 elements in that set. I mean, each element is a subset. This is the power set of B. There are 4 elements in there. And there's the power set of A intersect B, and that contains only 2 elements. Do you notice something interesting about these numbers, 2, 4, and 8? They are all powers of 2. And in fact, in general, if A has n elements, then the power set of A has 2 to the n elements. We might even write this as n of the power set of A. So the cardinality of the power set of A is 2 raised to the cardinality of A. And lastly, 3, set partitions. Let's suppose A is the set 1, 2, 3, 4, 5, and S is the set that contains the subset of 1, a set containing 2, 4, a set containing 3, 5. Something that's nice about S is that all of the numbers 1 through 5 appear somewhere. There's 1, 2, 3, 4, 5. And each of those numbers 1 through 5 appears only once. There's no overlap. So this collection of sets accounts for every element in A, and it does so only once. These are the key ideas of a partition. A partition of a set A is a set of non-empty subsets of A, called parts, such that distinct parts are disjoint and the union of all parts is A itself. So how about some practice here? Let A be the set 1, 2, 3, 4, 5, 6. So here are a couple of examples that are partitions. I can make the set of the set 1, 2, 4, 3, 5, and 6. So these subsets are all disjoint. They are all non-empty subsets of A, and every element of A is accounted for somewhere. The example in number 2 is a little more interesting. There's not much there. There's only one subset. It is the entire partition. So notice how it is a set that contains one element. Now these 3 examples are not partitions. What is it that fails? Why are these not partitions? Take a couple seconds, see if you can figure that out, then start up again when you are ready to check your work. Alright, so number 3, why is 3 not a partition? Well, the parts are not disjoint, so it looks like I can see a 3 here and a 3 there, not disjoint. How about number 4, why is 4 not a partition? It's not a set of sets. This 1 and 2 are just kind of hanging out. I guess if I had done something like that, then that would be a valid partition, or if we had put the 1 and the 2 into their own little sets, that would be a valid partition, but not as it stands originally. And the last one, number 5, why is this not a partition? The subsets of A are supposed to be non-empty, so we wouldn't include the empty set as one of those elements. Now, partitions become more interesting when I have infinite sets. So consider the set of all integers. How might I partition the set of integers? I want to do this in a way so that I have subsets that are disjoint and that account for every integer. So take a look at 1, 2, 3, 4. Which ones of these are partitions of the integers? Which ones are not? And once again, pause the video, do your best, and then unpause to see the answer. Okay, so number 1, yes, this is a partition. In fact, this is by the division theorem. So this is all multiples of 3, the one on the right, everything that's 1 more than a multiple of 3, and everything that's 2 more than a multiple of 3. Set number 2, not a partition. The number 4, among others, is missing, right? You'll see that among these 3 sets, none of them has a form that would account for the number 4. Also, the number 5 appears in 2 different parts. So in this first subset, the number 5 is in there, but also this second subset, the number 5 is in there too. So this proposed partition, number 2, that fails on a couple accounts. How about number 3? Not a partition. This is missing a few things, 3, 5, and 6, for example. On the other hand, these 3 sets do happen to be disjoint, so that's a start. And number 4, yes, this is a partition. The first 2 parts account for all odd integers, that's the 4n plus 1 and the 4n plus 3, and then the third part accounts for all even integers. Alright, so we've hit 3 big ideas: the Cartesian product of sets, the power sets of sets, and partitions of sets. Alright,